Okay, good morning, everyone. My name is Max de Savetas, and I'm joined here with Emily Matthews. We are both postdocs, and together we are the, or you might want to switch that to presenter mode. We're the co-chair of the newly established IGAC-iCACGP ECR Scientific Steering Committee. Before I proceed too far, at the bottom of your screen in the toolbar of Zoom, you're able to turn on the captions and select a translation if you might have some issue with English. So welcome to the first IGAC-iCACGP ECR conference. For those of you who might not be aware, IGAC is the International Global Atmospheric Chemistry. It is better known for its conferences, which happen every 2 years. It was before in Asia, in China in 2012, in Japan in 2018, and will be next year in Kuala Lumpur in Malaysia in 2024. You can find more information about the upcoming conference in the main hall of GatherTown. You can see on your screen the framework within which IGAC stands. So there is the International Commission on Atmospheric Chemistry and Global Pollution, standing right above IGAC, which was established in 1957. IGAC was established in 1990. And going up from there, there's the International Association on Meteorology, going all the way up to the International Science Council. IGAC also stands below Future Earth, which was established in 2015, which aims to bridge the gap between scientists and policymakers. At the very right of the screen where IGAC stands, you also find SOLAS and ILIPS, which are other organizations, which like IGAC help network all the community and all the scientists together. The main goal of IGAC, sorry, one slide back, is to facilitate atmospheric chemistry research towards a sustainable world. And IGAC does so through a number of activities and working groups, which we have outlined in the main hall, and you can find lots of different information about those. And they can help you find relevant activities or working group in your region for you to engage more with the atmospheric chemistry community. On to you, Emily.
And I'm presenting to you this year's IGAC-iCACGP Early Career Scientific Steering Committee. We formed at the beginning of this year, and for the past few months been working hard to bring you this conference, which I really hope you will enjoy and leave having made some new connections. And this is our first major event as part of our mission to reach, engage and support early career researchers within the atmospheric chemistry community. So moving on to the events of today and some housekeeping. All of today's sessions, except for the poster session, will be held in Zoom. The links can be found in the conference booklet, or you can enter via the appropriate room in GatherTown. For this morning's highlight talks, please use the Q&A function, which hopefully you should see at the bottom of your screens, and we will try and get through as many as we can in the allotted time. For the icebreaker, climate activity and skills workshop, we really encourage you to have your video and microphone on, as these will be interactive sessions. The in-person IGAC conference has always put on a great series of ECR events outside of the scientific network to facilitate networking, and we hope that these sessions will replicate these to some extent, and that by meeting some new people today, you will be able to make most of that poster session that we have at the end of the day. And just remember that if you're wanting to have your poster judged to be considered for one of our amazing poster prizes, to be your poster during your 20-minute allocated window.
So hopefully you got here through the GatherTown. This is our online virtual conference center. As I was mentioning before, the main hall is filled with spaces dedicated to the activities. That's the top of the screen, the working group on the inner top. You have information about those sister organizations on the lower left-hand side, and also our sponsors on the lower right-hand side. Currently, we've gone through from the plenary onto the Zoom webinar. For the interactive activities, you will have to make your way back up into the side meeting room, which links you to the Zoom meeting. And then, of course, there is the poster room where hopefully some of you have found your posters already and where the poster presentation will take place. You can interact with any of the items across all of GatherTown by just pressing the X button on your keyboard. And I do invite you to spend some time exploring. If you don't have time today, the GatherTown, will remain open till the end of the month. And then, next slide. We were lucky to obtain some sponsors for this event. This allowed us to fund the 6 poster prizes, which I remind you include the registration and travel to next year's IGAC in-person conference in Malaysia, the European Space Agency and Future Earth Together, the International Atmospheric and Meteorology Association, the National Center for Atmospheric Science, and Copernicus Publishing. And we also owe a big thank to the IGAC-iCACGP and IGAC scientific steering committees who are helping us today and make up a lot of the poster judges, and also Dr. Langley Dewitt, the director of IGAC, who helped us with a lot of the admin going on today. And with that, I think I will pass it on to Patrick to introduce our first speaker.
Morning. So so is my voice clear? Yeah, sure.
Yes, clear.
So the first Highlight Talks speaker here today is his name is Shahid Uzzaman. He's a PhD student from the Bangladesh University of Engineering and Technology. So today he's going to talk about the indoor air pollution in Dhaka, Bangladesh. So let's give him a very warm welcome.
Am I audible?
Yep, clear. Thank you. You can start sharing the screen.
Okay, thank you. Can you see my screen?
Yes, it's full screen. You can go. Thank you.
Okay. Thank you, IGAC-iCACGP, for giving me the opportunity to present my research work. I'm Shahid Uzzaman. I'm currently working as a lecturer at the Department of Chemistry, University of Bangladesh University of Engineering and Technology. And I completed my undergrad and master's from Department of Chemistry, University of Dhaka, under the supervision of Professor Dr. Abdul Salam. Today, I will talk about insights of indoor air pollution in Dhaka, Bangladesh. This is the overview of my presentation. I'll talk a little bit about the background of indoor air pollution in Bangladesh. And we have performed researches in different indoor microenvironments. And today I will show the results of 3 particular indoor microenvironments like home, school, hospitals, and finally the conclusion. So indoor air pollution. The growing concern about indoor air pollution is severe nowadays, as we all know that about 4 million deaths per year in 2020, and according to WHO, which includes about 237,000 deaths of children under the age of 5. Women and children bear the greatest health burden from the use of polluting fuels and technologies, and around 2.4 billion people worldwide, which is around 1/3 of the global population, cook using biomass and coal, which generates harmful household air pollution. You can see in this figure that the Southeast Asia and the Africa region has the highest deaths per million due to indoor air pollution. Now I will introduce a little bit about Bangladesh. Bangladesh is a Southeast Asian country surrounded by India from 3 sides and Bay of Bengal from the southern side. The capital city is Dhaka. And you can see that Dhaka is the central part, and we have like 8 divisions: Rangpur, Mymensingh, Sylhet, Chittagong, Borishal, Khulna, Rajshahi. And we have around 170 million people, current population, which is the 8th most populous country. The capital city, Dhaka, is the 4th most populous city globally with around 22.5 million people. Diverse economy with agriculture, textile, and remittance playing crucial roles in Bangladesh. And we have also a rich cultural heritage with diverse traditions, language, vibrant festivals. And the capital city, Dhaka, is one of the most highly polluted cities in the world. Talking about pollution, the air pollution scenario in Bangladesh is such that this type of headlines has become very common to us, particularly in the winter season. And air pollution in Bangladesh, the capital city Dhaka has recorded the 5th highest PM2.5 concentration among all the global cities in the world, according to the State of Global Air 2022 report. Air pollution is the 3rd leading risk factor for death and disability in Bangladesh in 2017. And according to this recent report, Dhaka has recorded the highest premature death from 2005 to 2018 due to air pollution. And Bangladesh has the highest all-cause mortality due to environmental risks among all the Southeast Asian countries. It's even greater than the average values. And of the total environmental health risks, you can see that the ambient PM2.5 and the household air pollution has the major share of all-cause mortality. Now, what are the sources of air pollution in Bangladesh? According to this report, brick kilns are the major sources of PM2.5 pollution in Dhaka. However, a recent research has found that vehicular emission and road or soil dust has the major share of the PM2.5 concentration. Now, indoor air pollution. About 90% of households in rural areas of Bangladesh use biomass fuels. And of the biomass fuels, wood is the commonly used, and also leaves, bamboos, cow dungs, and so on. Only 23% of the population has access to clean fuels and technologies. And in the urban household, about 50% use the solid fuels. And in Bangladesh, women spend around 3 to 7 hours in cooking and are getting heavily exposed to PM2.5 or PM10 concentration. And an interesting study was conducted in 2022 in 12 global cities in the world, particularly in the kitchen, has found that in the kitchen of Bangladesh has the highest PM2.5 and PM10 concentration, which could be due to the small kitchen volume, extensive frying, and prolonged cooking time. And now our first case study, which was performed in the indoor environment, particularly in the home. This study was published in 2019 in Environmental Science and Pollution Research. It has, this is the sampling size. You can see the capital city Dhaka, and in the Dhaka, they performed sampling in 4 residential areas: Rampura, Mirpur, Khilkhet, Dholaipar, and also Tongi. Now, Khilkhet is a heavily crowded residential area with also influence from traffic. And Mirpur is a construction site, and also traffic intersection, major traffic intersection are there. Dholaipar is a very crowded place with glass, plastic, and welding factories all over there. And Rampura is a moderate residential area with a moderate contribution of traffic. So this is the indoor particulate matter variation in different sites. They performed the sampled using the real-time concentration. We're using the Aeroset 531 series sampler. It's a real-time sensor-based instrument, which gives PM1 concentration, PM2.5, PM4, PM7, PM10. You can see that particularly in Khilkhet and Dholaipar has the highest PM concentration all over, and maybe PM10 concentration has a greater contribution in Rampura. And this is the indoor-outdoor ratio. You can see that the main indoor-outdoor ratio for all the sampling sites were around 0.76, which clearly indicate that the outdoor site has a major influence over the indoor PM2.5 concentration. This is the hourly variation of nitrogen dioxide and total volatile organic compound. You can see that the gradual increase of nitrogen dioxide concentration as the time goes by, which could be due to the opening of windows and also traffic emission, increasing the traffic emissions. There is this particular spike in around 14 to 15 p.m., which could be due to cooking activities. And you can also see that the gradual decrease of total volatile organic compound, which is because of the opening of the windows and doors, and eventually which increase the ventilation. And the association of ultrafine particulate matter with lung function, this is for PM1. The lung function was tested using a peak flow meter of the indoor residents. You can see that the negative correlation between PM1 and peak flow rate. You can see that the highest PM1 concentration were found in Khilkhet, but the lung function, the peak flow rate was lowest, which indicates that due to the prolonged exposure of PM particulate matter, the lung function has decreased in the indoor residents. Similar results were found for PM2.5 concentration as well. And finally, the determination of total health hazard ratio. Hazard ratio were identified using the measured concentration and dividing by the reference values, and the THR are the total, the summation of all the hazard ratios. This research found that Khilkhet and Rampura has the highest total hazard ratio, which indicate the major health risks for this region. These are the key findings of this research. This research found PM concentration exceeded the WHO and EPA standard limits in all monitoring locations. Indoor and outdoor ratio are found around 0.75, which indicated that the outdoor sources rising from vehicular emission influencing the indoor concentration. Negative association were found between PM1, PM2.5, and peak flow rate, which indicated the decreased lung function, and the average total hazard ratio were considerably higher in Khilkhet, which indicate that the residents in Khilkhet are more exposed to air pollution than others. So now moving on to the second case study. This study was performed in schools and published in Environmental Research Communications. In this research, we have collected samples from 10 different schools in Dhaka city. The schools were categorized into different categories, like in the residential side or in the industrial side, or near to a pond, near to a busy traffic interaction, and so on. This is the variation of particulate matter in indoor and outdoor of 10 schools. The left figure is for the indoor particulate matter concentration, and the right figure is for outdoor particulate matter concentration. You can see that the particulate matter concentration varied, particularly in S1. S1 is the school 1, which is the Kamulapur station, which has a heavily traffic influencing sites. And we also measured the peak flow rate of around 250 school children, out of which 60% were girls students and 40% of boys students. We measured their lung function using peak flow meter, and we also found that the peak flow rate were decreasing along the increase of particulate matter concentration, which clearly indicates that the higher exposure causing the decreased lung function of all the school children. The school children were, at the age of the school children was around 9 to 12. And this is the hazard quotient assessment. Hazard quotient's value should be less than 1, but according to this research found that the hazard quotient of PM10 were 2.5 indoor and 3.6 outdoor. And on the other hand, for PM2.5, average HQ were 1.8 in indoor and 1.9 in outdoor. So all the hazard quotient were found greater than 1. So these are the key findings of this research. We found relatively high particulate matter concentration at the school premises. Negative correlation were found with a peak flow meter, indicating that the health risks of the school children, and the HQ value also indicated the moderate health risks of these school children. And the third case study, the air pollution in the environment in hospital. This research were published in 2021 in Indoor Environmental Science and Pollution Research. We performed sampling in 3 different hospitals, hospitals A and hospitals B, the biggest governmental hospitals in Bangladesh. This is called Dhaka Medical College Hospital, and this is called Bangabandhu Sheikh Mujib Medical University. And the control site is a botanical garden, which is mainly a park. And Hospital C is a relatively rural area. This is also a governmental hospital. Why we concerned with government hospitals? Because generally the low-income people visit there, and these hospitals usually get the highest percentages of patients. This is seasonal variation. The research were performed in 2 different seasons, post-monsoon season, which is from September to November, and another season is winter, which is from December to February. You can see the PM concentrations in the post-monsoon season were around 50 microgram per meter cube, which is obviously higher than the WHO guidelines. However, in winter season, you can see the staggering concentration of PM 2.5 increasing around 5 to 6-fold in the winter season. This is the seasonal variation of trace gases concentration. You can see the higher concentration of carbon dioxide and nitrogen dioxide in the post-monsoon season. However, in the winter season, also nitrogen dioxide and carbon dioxide concentration clearly increasing, but total volatile organic concentration were found decreasing compared to post-monsoon season. This is the indoor-outdoor correlation. This top is for Hospital A, this is for Hospital B, and this is for Hospital C for indoor versus outdoor PM1 concentration. You can see that we found a good positive correlation between indoor and outdoor, which indicate outdoor environment is potentially influencing the indoor environment. Similar results were found for PM 2.5 and also PM10. This is indoor-outdoor ratio. You can see that the average indoor-outdoor ratio were found close to 1, which again indicates that the presence of influence of outdoor environment to the indoor environment. And toxicity potential. Toxicity potential is mainly the ratio between the measured concentration and the guideline values. For guideline values, we used WHO 2021 guidelines, which is 15 microgram per meter cube for PM 2.5 and 45 microgram per meter cube for PM10. TP value should be less than 1. TP value greater than 1 indicates the specific potential pollutants may pose severe health concern. We found that in the post-monsoon season, except 1 or 2 sampling sites, all the sites TP was greater than 1. However, in the winter season, you can see that the TP value increased from around even 15 times greater than 15 times higher, which clearly indicate the high health risks for the hospital patients. So these are the key findings. We found particulate matter concentration very high, exceeding both national ambient air quality standard for Bangladesh and WHO guidelines. We found high indoor-outdoor ratio and strong positive correlation between indoor and outdoor particulate matter concentration. And we all found that the toxicity potential was exceeded 15 times higher than the normal. And this is the summary of my talk. I found research across homes, schools, and hospitals indicated the presence of severe indoor air pollution in Bangladesh. Elevated concentration of particulate matter were found, surpassing WHO and EPA standards, and a high particulate matter concentration within school and hospital premises raised concern for the health of students, patients, and staffs. Indoor-outdoor concentration were found heavily influenced by vehicular emission. Negative association between PM1, PM 2.5 with peak flow rates suggest potential health risks. And we suggest urgent intervention and policy measures are needed to address indoor air pollution in various settings. Thank you.
Brilliant. Thank you so much, Shahid, for that great talk and for keeping on time, which means we do have some time for some questions. So there are already some in the chat. Everyone else, please feel free to continue popping your questions into the Q&A function. So the first question is asking about how does agricultural residue from burning and also transboundary air pollution influence the PM 2.5 concentration in Dhaka?
Yeah, thank you for the question. Yes, agriculture residue burning heavily influence in the PM2.5 concentration in Dhaka. We have another research which shows that about 40% of total PM2.5 concentration in the winter season is influenced by the transboundary air pollution. However, we haven't shown this research here, but it's heavily influenced by the transboundary air pollution.
Thank you. And our next question is, which PM, PM1 or PM10 was more responsible for reducing lung function in indoor air?
Both has a major influence, but PM1 directly goes inside in the bloodstream and causes more health risks compared to PM2.5.
Thank you. And our next question, regarding the source of the outdoor pollution, did you try to investigate the influence of PM transport using, for example, a back trajectory model or another method?
Yeah, I have performed back trajectory model. It shows that the pollution mainly coming from the outdoor sources, as the hospitals or indoor schools does not have air filters there. So the vehicular emissions clearly is contributing to the indoor air pollution.
Thank you. We've got lots of interest in this talk, which is fantastic. And our next question is, do you assess the short or long-term exposure of PM2.5? If so, what methodology do you follow?
I haven't still done the long-term exposure of PM2.5. This is in work in progress. So I will like to share it later.
No problem. And then someone asking, how do you make the link between lung function and the particulate matter? Is this sort of based on hospital admissions or some other data?
Not really hospital admission. This lung function, a link between lung function and PM particulate matter were based on the peak flow meter rate. Is a sophisticated instrument which measures the lung function as the exhale ability. It shows the data around for a healthy person, peak flow rate should be around 500, greater than 500. But we found that in the school children, about 50 to 60% school children has asthma, so their lung function were really low. So it's not based on the admission to hospital.
Thank you. And I think one of your earlier slides, you showed a negative correlation between PM2.5 and PM10. What does this negative correlation indicate?
Negative correlation indicates that due to the increase of PM2.5 concentration, the resident has the lower lung function, which decreases the peak flow rate. So one is increasing, another one is decreasing.
Thank you. And our final question, you're doing very well. Does the meteorology influence pollution concentrations? If yes, how do you determine the sources and locations of the pollution?
Yes, meteorology has also strong influence in particulate matter concentration. To identify sources, we have performed in different study positive matrix PMF modeling, which indicated the sources, but I haven't shown it here.
Thank you. And I think one of our committee members, Martin, would like to ask you a question, if that's okay.
Yeah.
Yes, thank you for this very interesting talk. On slide 13, you showed outdoor-indoor infiltration ratios also for PM, and there was, I think at 14 o'clock, there was an outdoor-indoor ratio above 1 for PM. Can you, do you have reasons for that in maximum? I think it was not the average, but in the maximum. Is there a reason for that?
Yeah. Because usually the indoor-outdoor ratio remains less than 1 because the high outdoor concentration is obviously greater than the indoor. But particularly that time, that there was cooking activities going on, so it increases the indoor concentration as well, and that's why the ratio were close to 1.
Okay, thank you. Thanks again for your talk.
Thank you so much.
And with that, I think that includes our first highlight talk of this year's conference. So thank you very much, Shahid, for that really insightful talk and for answering all of those questions so well. And with that, I think Max will welcome our second speaker.
Sure. So our second speaker is Dr. Beata Picosa, or Bea. Originally from Serbia and Hungary, she came to Australia to do her PhD at the University of Wollongong, where she studied the apportionment of methane in geochem, if I remember correctly, and then moved on to do her postdoc at NIWA, the National Institute for Water and Atmosphere in New Zealand, where she's been studying the carbon cycle and trying to account for all the sources and emission sequestration. And with this, Bea, if you're ready, I will let you introduce your talk.
Thank you. I'm assuming that everyone can see my slides. Yeah, so thank you for the opportunity to present, and also thanks for the whole team for organizing this conference. I can only imagine how much work that involved. So as Max said, I'm going to talk about some exciting new research in New Zealand through our two main research programs, Carbon Watch and Methane Set, as well as the importance of this work globally. So I'll start with Carbon Watch. So Carbon Watch is a project with an aim to quantify net greenhouse gas carbon fluxes on a different spatial scales, so national, regional, and urban scale. So under the UNFCCC, countries around the world report their greenhouse gas emissions. For example, in New Zealand, the Ministry for the Environment compiles New Zealand's national inventory each year. And these estimates are based on bottom-up methods. What we do in Carbon Watch is that we use top-down methods or inversions to estimate the same numbers. And we do this for carbon dioxide and for methane. So how does an inversion work, greenhouse gas inversion? And I'll use carbon dioxide as an example here, but the method for methane is basically the same. So we use a Bayesian approach to estimate net air land and air CO2 exchange, and we do this on a weekly scale for different geographic regions, as shown on this figure. And there are overall three main components to the inversion. So the first component are the CO2 measurements in the atmosphere, and in our approach, we use measurements from two sites. So the blue dots on these figures, they represent the afternoon measurements at these sites, while you can also see an orange line that represents the background CO2 values, which are predominantly oceanic air. And that means that the background data, they represent the CO2 amounts outside of New Zealand, while the blue dots, they describe what is happening inside of New Zealand. And what we use for the inversion is basically the difference between the two. And if you look at the blue versus orange lines, what we see in this data is that the background CO2 is overall higher, suggesting that New Zealand is an overall carbon dioxide sink. But of course, we need the inversion to know how big and estimate how big the sink is and also its origin. So the second component that we need to run the inversion is a first guess of the fluxes, and we use prior terrestrial, ocean, and fossil fuel fluxes. And the third component is a transport model. And we use the name-free Lagrangian dispersion model, which we drive with a local configuration of the UK Met Office unified model. And we basically need the transfer model to get information about the pathway the air took prior to arriving to the two sites. And this is very important because air coming from different parts of New Zealand will have different CO2 signature. And we basically need to link each measurement point with the regions or the land types or the fluxes that potentially influence that specific CO2 signal. So what did we find out when we ran the inversion? So the results of the inversion, and these are for the on a national scale, so they are shown in green, while the gray shows the prior estimates. And as you can see, there are some quite big differences between the numbers. And overall, the inversion suggests that there is a stronger carbon uptake on a national scale. And in addition, the national inventory values are around 30 teragram of CO2 per year. This is a sink, which is also quite different from what both the prior estimates and the inversion suggest. Now, an important thing to note here is that these methods are not, they're fundamentally different. So these numbers are not actually directly comparable. So to resolve some of these differences, we work together with MFE, who compiles the national inventory, to understand all the things that could lead to these differences, which is a quite complex process. But let's go back to the inversion results. So When we looked at the spatial distribution of the net fluxes, we saw that the largest sink signal is from a region called Fjordland, which is in the South Island. And the interesting thing is that this region that is covered by mature indigenous forest. And what the inversion was potentially suggesting is that these environments might be a more efficient sink than what we thought before. And this is not something that, for example, MFE would guess when they compile the national inventory, since traditionally we would expect stronger sink from younger exotic forest relative to mature forest as we have in Fjordland. So exotic forests are fast growing and they sequester carbon quickly. However, they only last a few decades, while native forests, they remove carbon at a slower rate, but they can continue to sequester carbon for hundreds of years. And this reason is also why New Zealand's Climate Change Commission, in their report, recommended the increase of native trees, because they basically provide the long-term carbon sink. However, if indigenous forests can also take up more carbon than what we thought before, this can actually have an additional impact on how we're managing land in New Zealand or globally. And overall, it would have an impact on mitigation strategies. So to understand what is happening with the carbon sequestration, and basically the roles of forest, grasslands, and other impacting factors, as for example, pest eradication, and overall to understand better why things are different at the places where we see these big differences. We also work together with the terrestrial biosphere community in New Zealand. We are expanding our measurement network, and we perform smaller scale and regional studies. And we also measure additional carbon exchange tracers such as CO2 isotopes or carbonyl sulfide. And these measurements are very important because they directly carry information about the actual processes that drive the carbon fluxes. Now, of course, there is also the question of what if the results are impacted by some biases or errors in the inversion system. So we did a quite large number of improvements and tests to our system. So the main idea with these updates and tests was basically to try and challenge the inversion with everything that we can think of. So by changing the inputs or the setup, and see how all of that impacts our results, and to see if that sink that we see in the inversion is still there. And this is a summary of some of the main things we did, which includes updating a transfer model from a 12 to a 1.5 kilometer resolution, which is actually a significant update, and also an important one due to quite complex terrains in New Zealand. We tested different priors, different land cover maps, different background CO2 values, and other things. But so far, no matter what tests we did, the sink was always there. And we also have a PhD student who is now implementing additional updates to the whole system, as adding new measurements, improving the whole inversion statistical framework, adding improvements about the CO2 diurnal cycle, which we find to be quite important, including nighttime measurements, because as I mentioned, my setup was only based on afternoon measurements, as well as solving the whole inversion system for GPP and respiration separately instead of optimizing the net fluxes. So that was an overview of the carbon dioxide results. And as I mentioned, we also perform national scale methane inversions. And this is work that is performed by a colleague of mine, Alex Geddes. And in contrast to CO2, where the results are quite surprising, for methane, there are no big surprises. So the inversion replicated the prior estimates and the methane inventory. And these results definitely additionally highlight the potential value of using these techniques in verifying inventory estimates and methods, as well as mitigation strategies. And for example, the results for methane are already being used in New Zealand to inform the bottom-up national inventory. That was a quick overview about Carbon Watch. And now it is time to talk a little bit about MethaneSat. So MethaneSat is a new methane observing satellite with a launch date in early 2024. And it involves partnership between the US and the New Zealand government. So the core mission of the satellite is to support emission reductions globally by detecting methane emissions from oil and gas leaks. While the New Zealand science team's aim is to use the satellite to detect agricultural methane emissions and also test and develop the methods that are needed to quantify agricultural methane emissions which is not an easy task, and I'll explain later why. So what is interesting about MethaneSat is that it's quite unique satellite. So we currently have satellites that can detect methane globally. They produce excellent methane data on a global scale and also a regional scale, as well as point sources. However, they're unable to provide accurate information about sources on a smaller spatial scale. Then we also have satellites that focus on smaller areas and specific location, and they provide amazing data about point sources all the way down to facility level. However, the problem is that they can't provide information about total emissions and for specific areas or regions. And MethaneSat is special in a way that it can fill the gap between the global and the specific location mapping satellites. And that is because it has a really wide field of view and also high level of precision and spatial resolution. And because of that, we can use MethaneSat to quantify the total emissions, since it can detect both the dispersed area and also the concentrated point sources. So the US science team's focus is on the development of the tools and all the infrastructure that is needed for the oil and gas sources and the identification of the targets, while, as I said, the focus of New Zealand's science team is on agriculture. Now, why agriculture? So we know that agriculture is responsible for more than 50% of the total anthropogenic methane emissions globally, and methane emissions in New Zealand make up nearly half of our gross emission budget. And also 85% of these methane emissions are just from agriculture. And this is a quite unique greenhouse gas emission profile for a country. And it is also one of the things that makes New Zealand an ideal natural laboratory to develop and also test these capabilities. So what we do is we're working on identifying, ranking, and selecting the global agricultural targets. We also work alongside the US team on the retrieval algorithms for all applications, which basically includes a detailed comparison of these algorithms across different instruments that are going to be used as part of the mission. And the main thing is what we do is that we're trying to better understand the agricultural methane signal in the atmosphere. We're trying to map the agricultural emissions based on the satellite data, as well as other model data that I'm going to show later, all prior to the satellite launch. And we also work with the US team on adapting and developing the level 4 methods for agricultural sources, which can be quite challenging. Now, why are these things so challenging? So methane fossil fuel emissions, they tend to be strong point sources, and they tend to form clear plumes that are much easier to absorb from space and also to quantify. On the other hand, agricultural emissions and pastoral agricultural emissions that we have in New Zealand, they are much more diffuse. And relative to oil and gas, these are weaker emissions over larger areas, which makes them much harder to both detect and also to estimate with the different methods we have. Now, as I said, MethaneSat is not yet launched. However, Methane Air is operational, which is basically an aircraft that has an instrument that is very similar to the one that we'll have on the satellite. And we already have data from the aircraft that serves as an amazing preview of what the satellite will see. And the two figures here show an example of an oil gas versus an agricultural. See, the agricultural one is quite diffuse, which again will be quite challenging to estimate. However, New Zealand has a number of advantages when developing these tools, both to map the diffuse agricultural emission and to understand better what this means to us. As already mentioned, methane emissions in New Zealand are dominated by the single source, which is agriculture. So the source attribution is relatively easy relative to other places. We have a strong ground-based methane measurement network, which we will also complement with additional field measurements once the satellite is launched that will help us additionally validate the results. And these measurements include in situ and flask measurements of methane and also methane isotopes, eddy covariance measurements of fluxes at paddock scale, and also ground-based remote sensing measurements and aircraft measurements. And we also have a high spatial resolution transport modeling capability and high resolution bottom-up emission maps, and also semi-operational national inverse modeling, as I already mentioned as part of the Carbon Watch project. Now, Currently, we don't have measurements like methane air across New Zealand. However, we do have some modeling results that we use to better understand what we can expect to see with the satellite. So to model the methane column enhancements from agricultural processes, we combined 1.5 kilometer agricultural methane fluxes with transport model simulations from the NAME model. So this is the same model as we use as part of Carbon Watch. And then we use these modeled column values to better understand the impact of the level 2, so the retrieval algorithms, and also the level 4 processing. So in terms of the level 4 methods, which are basically the methods that will take the satellite data, so the atmospheric concentrations, and convert it into what we're interested in on policy levels like emissions. So in terms of these methods, there are a few approaches that will be used for oil and gas targets, depending on the type of the source. So if the satellite observes a plume-like source or a more of an area or diffuse source. And our main focus for the agriculture will be on adapting two methods. One is called the divergence integral method, and the other one is a geostatistical inversion approach. And these are some of the modeled column enhancements for one of the New Zealand targets called the Waikato. And these are results for the three different wind conditions. So the first plot represents the emissions used for the calculation. The second column shows the wind speed and the direction, and the third column shows the resulting methane column enhancements. And also note the plots have different axis limits. And based on these examples, we can see an expected relationship between the atmospheric methane values and the wind conditions, with higher enhancements for scenarios when we have lower wind speed, and also lower enhancements during strong wind speed conditions. And in the middle plot, you can also see a target with a more diffuse signal, while the top and the bottom plots suggest that a plume-like agricultural signal can be expected under specific wind conditions, similarly to the oil and gas sources. And overall, what these plots highlight is the importance of choosing or finding the wind conditions that are optimal for observing strong enhancements, and also spatial gradients that we need for better emission estimation with the different level 4 methods. And those were some examples for one of the targets. However, in New Zealand, we have a total of 4 main methane set targets. And these are some of the example snapshots for each of those. And again, we observe different behavior in the atmospheric signal depending on the meteorological conditions, including both plume-like and diffuse scenarios. For New Zealand specific agricultural fluxes, we roughly observe enhancements from 1.5 to 12 ppb, which is beyond the satellite detection limit, which is good. And there's quite a bit of information in these simulations, which is exactly what we were after, because the aim of all of these modeling work is to better understand the atmospheric signature from agricultural processes and how well we can estimate those values. And yep, that would be a quick overview of our main work, greenhouse gas work, and I'll just leave the summary slide up and happy to answer any questions.
Thank you very much, Beata. That was a very interesting talk. We have already a few questions, but if there are more questions, please just enter them to the Q&A system. So first question, or the first two questions, are referring to your baseline for CO2. So how did you define the CO2 baseline? Is it basically the minimum values? And what is the methodology to select the baseline?
Yeah, so selecting the baseline was a quite interesting process, and there are a few methods that we try. So first of all, one of those two sites that I showed, Bering Head, is actually a baseline site. So it has baseline conditions that are defined as there's no contact of the air with the land, some really tight constraint on CO2 variability, and basically we use those baseline conditions and days as our background inflow. However, that was not the only thing we did, because we also tested, because Bering Head is basically, it's capturing the baseline conditions where the air is coming from the south. So there was a question, what happens if the airs come from the north? So that would create a bias in the inversion. So we additionally merged these measurements with measurements from ships, from the TF5 ship campaigns, which are basically CO2, greenhouse gas measurements between Australia, New Zealand, and Japan. So that was kind of a northerly and southerly baseline. And we also tested using modeled values around New Zealand to define the background from the carbon tracker model. However, no matter which one we used, this sink was always there. So in our case, we found that New Zealand it's not that sensitive to the selection of base loss conditions, but this might be different for some other countries.
All right, thank you. Next question is, what plays an important role in the agriculture emissions? Is it more the irrigation or more the chemicals?
Well, in our case, for New Zealand, we really focus on manure management and the emissions from the ruminants, where ruminants play a bigger role. However, there are quite big uncertainties in some of these approaches that on a farm level that people use, and we hope that we're going to get additional information on how to solve and what's the impact of these different methods that are being used.
Okay, next question is how methane air responds in diverse topography.
So as every satellite, when you have a complex topography, the results can be biased a little bit. Now, with methane set, the good thing is that it's a really high spatial resolution. So we're hoping that we can leverage that to get better estimates. And also we will target the same region over and over again. So again, that will improve our trust in those results.
All right, then we have Claire Murphy, which says, first of all, great talk and thank you. And she has a question about the CO2 sink. Why was it expected that young trees would absorb more CO2 than mature forests?
Yeah, good question, Claire. So this only comes down to the fact that those trees they grow faster, which means that every year they're just taking more and more carbon. While the native trees, they're basically in this equilibrium, so they don't really do much. They don't grow, which means the uptake of CO2 and the respiration of CO2 is basically in balance. So they don't they don't serve as an additional sink. All
right. Then we have, okay, I'm trying to say the name correct. The Priyanka Srivastava as a question for you. How do you expect that adding the new measurements and incorporating diurnal variations will affect your results?
Yeah, very good question. Well, with inversions, the more measurements have, the better, just because at the moment, I only showed the example with the 2 sites. Now we have measurements from 5 sites. And the importance of that is, for example, if one of those sites the measurements don't cover some parts of, for example, New Zealand, and your prior information is not that good in that area, the inversion won't adjust that, just because there's nothing to adjust it based on the measurements. So as you add new measurements, your confidence in those results will increase. Now, in terms of the diurnal cycle, this is very important in areas, for example, where you have forests, just because CO2 has a quite strong diurnal cycle. So if you ignore this component, your inversion result can be biased. With our 2 sites, we were lucky in a sense that both of our sites are not around a big, forested region where this diurnal cycle would impact things. However, some of our new sites are in the middle of the forest. And because we use afternoon measurements only and not nighttime, and there's another reason for that, you basically can bias your results toward a bigger sink.
Okay, thank you. And I think we have time for one last short question, which comes from Sindhu S. How to account for the role of VOC chemistry?
Okay, interesting. So with CO2 inversions, basically what people do is they ignore the chemistry part. Of course, CO2 is produced chemically through methane and with OH, and then through CO and other non-methane VOCs. However, when you compare those numbers with the numbers that the land processes that release and take up CO2 and the ocean and some the fossil fuel component, those are really small. The impact of the chemical production is really small. So basically, usually we ignore it, but you can also include it similarly as we include sometimes biomass burning.
All right. And thanks again for this interesting talk and this nice Q&A round. And I think I hand over to Patrick to introduce the next highlight speaker.
Thank you, Martin. So the last highlight talk speakers for the Asian Oceania session is Dr. Jiaru Li from Kyoto University in Japan. And today she's going to talk about the HO2 update onto the aqueous inorganic aerosols. And let's give her a very warm welcome.
Okay, thank you so much, Patrick, for introducing me. And I'm going to share my screen. So can you see my screen? My PowerPoint?
All good.
Okay, thanks. Okay, thank you. So I'm really very happy to introduce some of our group's latest work in the first IGAC-iCACGP ECR conference. And before my presentation, I want to thank Professor Dr. Ishino Sakiko for recommending me, and also want to thank Max, Patrick, Emily, and all the community members for organizing this great conference. So I will start. For the background, as introduced by Busako, there are nature emissions like emitting VOCs, volatile organic compounds, methane, and aerosols. And also we have anthropogenic emissions like human activity, also agriculture. So all those emissions in the air, when there is solar radiation producing energy, there will be photochemical reactions to generate secondary organic aerosols and also ozone. Those secondary products, actually, they are very harmful to human health and the vegetation and the ecosystem. So if we look into the photochemistry part, we will know there are actually a group of active species, also known as Hooke's radicals, including OH, HO2, and R2. Those radicals, they have an unpaired electron at the outer orbit, therefore they are active. The reaction of OH with VOCs and NOx, they initiate a radical propagation cycle and leading to the production of ozone and SOA. So if we want to well understand the behavior of Hooke's radicals, we know there are sources and sink of radicals. Normally, there are three patterns. One is the radical interconversion, like from OH converting to RO2, then to go through HO2 back into OH. This is radical interconversion as shown in the black color. At the same time, there are well-known gas phase reactional sources. We have module contains over 10,000 of chemical reactions. And also, we have gas phase reaction sinks of those radicals as shown in red color. Except those will understand the radical source and sinks, we are wondering if there are other possible source and sinks that are not well understand, not considered. So before giving out my scientific question, I want to introduce some literature review. Here, the left figure shows a recent conducted field campaign. They measure the concentration of OH, HO2, and the sum of HO2 and RO2. In the daytime, they found that the measured data, for example, in the case of HO2 radicals, the black line is the measured data, and they compare with the model either in red or in blue lines. They found that there are overestimates of the HO2 radicals, but those discrepancies can be offset by adding an extra HO2 loss, as shown in the green line. So the model studies, they are using, they try to using assumed uptake coefficient of HO2. Here they use the gamma value of 0.2 to see what kind of influence will those part be. At the right side, they're using the gamma of 0.2 to figure out the total Hooke's loss, and found that in 1997, the air source, like in the biomass burning locations, they will have a lot of air source. It can cost to around 70% of the total Hooke's loss, like in India and in the Arctic region in March. When it comes to August, it will be in Sahara and in Latin America and Africa. So this is a model result. You might wonder what kind of influence will those HO2 uptake make to the ozone production. Here, I want to introduce two research. The left side, they compare the ozone NO2 and PM concentration before and after the COVID-19 pandemic lockdown. The x-axis is the day of the year, and the vertical line shows the lockdown started day. So they compare the 3 years before the COVID-19 from 2017 to 2019, as shown in the pink line, with 2020 in the city in Wuhan. And the ozone actually was sharply increased around 36%, but NO2 and PM2.5 decreased. This means we have some unknown mechanism for ozone. So at the right side, also the model group, actually this paper was quite famous. And they found that in China, in the North China site, there is unknown ozone increase. So they investigate each driving factor individually and found that the PM changes was the main reason, especially the HO2 uptake could drive the increased ozone concentration. So here comes to my scientific question. I have two questions. One is to determine the HO2 uptake coefficient, and to figure out what is the key factors. And second is to understand, is there any uncertainty from HO2 uptake to the ozone production? To answer the first question, I will introduce our group's latest publication. This was also selected as the front cover of the journal. And simply put, for the conclusion, we found that the HO2 uptake could be faster if we have the air source contain transition metal ions like copper or iron. And so I will introduce the target and purpose of this part of HO2 uptake onto inorganic air source. We wanted to quantitatively investigate the HO2 uptake mechanism, including the uptake coefficient, how fast is the uptake taking on, and also the surface accommodation factor, the collision rate of the gas phase into the air surface, and the kinetics in the air surface. In the bulk phase, there will be reactions. We want to know some information about that. And also the aerosol properties, the impact. Our work is the laboratory work, and those factors, those parameters can be used in model study and also in field work. So before I introduce the methodology, I want to show previously the laboratory work, they also measure the HO2 uptake using the method of reactor combined with a detector. Usually, for the reactor, they choose the aerosol flow tube. There is an injector, so you can change the injection location of HO2 radicals. And by varying the injection location and flow rate, the residence time of aerosol and HO2 will change. At the same time, you can detect using some detectors, detect the HO2 corresponding concentration, then you will get the HO2 uptake. But this method takes time because you have to handle both reactor and detector. And for our method, we use the laser pump and laser-induced fluorescence technique. It's a pump flash of ozone to convert into OH radicals, then generate HO2. We inject the air source from atomizer in the reaction cell, and every second we regenerate HO2 radicals to interact with the aerosol, detect the HO2 reactivity as OH reactivity, because we inject NO to reconvert HO2 back into OH and to determine its fluorescence decay rate. This is how our instrument look like. And to give an example of the result, I compared the loose rate of radicals reactivity without any air source in the reaction cell, and by injecting a known volume of air source, you would get the exact loose rate of aerosol uptake by using the exponential fitting function. And from this K prime value, because we measure the surface concentration of air source, we can know the gamma value, the uptake coefficient directly. And our instrument limit of detection is 0.01, but this value should depending on the concentration, total concentration of air source you injected into the reaction cell. And for time resolution is around 2 to 4 minutes. After we get the uptake coefficient, we need to break down it into several processes. We're using the traditional resistance model to investigate it, assuming that the air source itself is in steady state condition and also it's inside the homogeneous mixed. So the gas phase HO2 radicals will firstly go through the gas phase diffusion and then call it as the surface and then enter into the air source to either take on bulk phase reaction or take on bulk phase diffusion. Those parts can be summed up to equal to the inverse of the gamma value. So as shown by these equations, it's like the electric circuit that consisting of the resistance. So we can get all the factors as we want. And to show the result, firstly, we compared the uptake coefficient we measured with previous determined gamma value. And our value is here. You see, it's quite good agreement from ours with previous. This result was based on the aerosol of ammonium sulfate. But in this case, I compared the gamma value with initial HO2 concentration because each system generates HO2 radicals maybe by a different way. So they will have influence. And in the case of HO2 uptake onto ammonium sulfate, the self-reaction is the main driving factor to dominate the loss rate. And still we have uncertainty. One thing is that we didn't measure the exact concentration of HO2 in our system. So there will be like the maximal is 10 to 10, but our system might be smaller than that. Another is the pH of air source. Here I plot two lines come from the theoretic line, assuming one pH of the air source is 4, another pH of the air source is 5.2. The green marker shows the good agreement with pH equal 5.2 because they did the experiment with pH buffer to the liquid when preparing the ammonium sulfate liquid. And then using the same way, we measured over 10 types of air source to report as much as gamma value we want, and found that regardless of the aerosol type, we found very limited uptake of HO2 with pure inorganic air source. But when you add the doped transition metal ions, the gamma value could be increased, like up to the maximal is from NaCl with copper is over 0.7. And the gamma value from copper doped is much larger than that from iron. And also, we did the experiment with two different types of seawater collected from Japan and found quite large variations in gamma value. One is around 0.1, another is 0.2. And here, the table shows the summary of all determined gamma value, and we compared with reference gamma value and picked from quite similar conditions that with the experimental. And for the first time, we reported many gamma values. So from here, I'm going to introduce the second part. It's about how can we use those HO2 uptake value related to ozone production. Also, I want to introduce some previous research. For the first one, they did some model simulation and to check the change rate of ozone that was caused by switching off HO2 uptake, which means they consider the total ozone production with HO2 uptake compared to without HO2 uptake. In the time of 1950, which is before the pre-industrial, there was almost no big change. But it come to 1970s in European and USA and also Japan, there will be around 10 to 20% come from the HO2 uptake. And more recently, the main change to China and India. It's around 20 to 13%. as we all know, the generation of ozone, there are two regimes for ozone production. One is VOC limited, another is LOX limited, depending on the ozone procausal's domination. But recently, a research group, they proposed actually, except VOC limited and LOX limited, they should be aerosol inhibited regime, which emphasizes the HO2 uptake's influence on ozone production. So we actually use the HO2 uptake factor measured in field study to check the influence on ozone. Here, left figure compares the maximal ozone production potential with NO concentration. In the case, the red dots show that when we consider HO2 uptake compared to blue dots without considering HO2 uptake, and we found at the condition of NO less than 1 ppb, there will be quite important reduction of ozone production potential due to HO2 uptake. And a simulation was also conducted. We use the average parameter of the daytime in some condition and found that with the HO2 plus the RO2 concentration during 10 to 100 ppt, the decreased percentage of ozone could be around 10% if you consider both HO2 and RO2 uptake. So, but this only uses the average concentration of the ambient air. We have no idea what will it be if we use into the field work. So I use the field work data set to check how much ozone production could be influenced by using our last year's campaign data conducted in Japan in Tsukuba. And we found that the HO2 and RO2 concentration were detected as the black line, and the real-time ozone decrease rate were showed as a dashed line, and actually the uncertainty could be quite large. It could be like someday around 70% or some days 2%, depending on the concentration of XO2 and also the NO concentration. So in this case, I didn't use the variable HO2 uptake, but use an average HO2 uptake coefficient with average assumed aerosol surface concentration. And so how can we better use those results? Once we got the uptake coefficient of HO2, we have the aerosol mass concentration and aerosol chemical property. We can use those factor into chemical transport model and know very broad, precise spatial temporal variation of the radical performance to understand the ozone production, SOA production, and also their influence to climate and to the geochemistry. And here will be my conclusion and outlook. I think my talk is more about the laboratory work. If you are interested, I will also introduce the relative humidity and pH dependence of the HO2 uptake in the post section. You can come to find me at the Gather Town. And lastly, I wanted to acknowledge my supervisor and all my collaborators in Japan. Thank you so much. I guess I still have 1 minute.
Yes, you're right on time. You happy to take some questions? Happy for some questions?
Okay, I guess I have two from.
Yes, so someone is asking, during lockdown, ozone is increasing, but PM 2.5 is decreasing, and then NO2 has no significant trend. Do you have an idea why that is?
Yes, actually, this is like one assumption is because of we have less PM, which means we have more radicals in the air due to the reduction of uptake. Then we can have more radical reaction to generate ozone. But there is also some other papers they mention during the lockdown. Actually, the weather the year weather you have to consider because it's more warm. Maybe we have less anthropogenic emission, but at the same time we have more natural biogenic emission that will also contribute to the photochemical reactions to produce the secondary products. So it's a little bit complex. But I trust that HO2 uptake also work to some extent.
Thank you. And the next question from Priyanka. Is there a dependence on the type of aerosol in respect to aerosol inhibition effect on ozone?
So it's the type of aerosols. Currently, we only did experiment on inorganic aerosols, but in the ambient air, actually aerosol itself is quite complex, not only inorganic, but also organics is a mixture. That part influence onto the inhibition effect of ozone actually is unknown. I can only say based on our experimental results, the inorganic aerosols with copper or iron or maybe even other like seawater sprays, they could be important in the remote ocean area. But when it comes to a mixture of SOA with organic, maybe the results could be different.
Thank you. The next question is from Claire Murphy. Is transport the dominant source of PM 2.5 NOx and CO, or are there domestic sources that potentially have increased during lockdown?
Transport like from the emission from vehicle can make some contribution to PM NOx CO. But I think it really depends on the location. For example, in Bangladesh, we still have very severe air quality problem. But in Europe, in Japan, I think the more strict emission standard has been taken on. So I believe the ambient air in those developed countries, they are much more, how to say, the air quality change has been changed. It's different, so case to case. I think maybe my explanation didn't answer well.
That's not a problem. I'm sure you and Claire can find each other in GatherTown if you want to chat a bit more. I had a question as well. Are there sort of specific regions in the world where you think the role of copper and iron will be important, perhaps because they have high emissions?
Yeah, the reason why we choose copper and iron is because actually in the ambient air, they are abundant. Like copper, iron, I don't remember ratio. I think iron is more abundant than copper, and both can be found in seawater. You know, at the surface of the ocean, there will be the ocean spray produce a lot of aerosols, and there must be some photochemistry taking on, but that part is not well recognized. So still there is something we can do. And of course, in the future, we also wanted to check more different chemical property of the aerosols, and it's just the beginning, a start of this part of work.
Thank you. And I think our final question would be from Sharon. So thank you for the great talk. And would you consider to incorporate the effect of aerosol size or surface area on the uptake efficiencies of these radicals? And then also, would you think that the reduced aerosols during COVID may in part contribute to the increased ozone due to limited sinks of the radicals on aerosols?
Okay, thanks for this question. So the effect of aerosol size and surface concentration, actually to the perspective of HO2 uptake, surface is more important. I mean, if there are more surface, which means the aerosol can provide more support for HO2 to be absorbed. But for the size, we haven't done the size dependence of uptake part, but it could be valuable to conduct that kind of activity. And to the second question, the COVID-19, the reduced air source, should be maybe model people can try to consider that part and to figure out if there are any inference due to the reduced air source, and more radicals, the further inference in the air. Yeah, I hope I kind of answer your question.
Brilliant. Thank you very much. And thank you again to all of our speakers for their really great talks and answering all of our questions. And with that, that is the end of our first set of highlight speakers for this year's conference. And this is where we temporarily say goodbye to our mid-career and established scientists. We hope to see you all later in the poster session. And to the ECRs, we hope to see you in the side meeting room in Gathertown in about 15 minutes at 4:40 for our icebreaker. So thank you very much, everybody. And we'll be getting on to a quick break now.